All right, we're going to begin the second topic in Bio 23, which is general chemistry. Now, I hope, as you'll recall, last time we talked about the hierarchy of living things, where in order to understand an organism, we had to understand its systems. And to understand its systems, we had to understand the organs and the tissues and the cells and so on. Most fundamentally, we have to understand atoms and how they work in order to understand any of the levels that come after it. So that's where we'll begin. Now, before we get started, I want to make a couple of terms clear. You will hear me use atom and element almost interchangeably, but I want you to know what they mean. An atom is an individual unit, an individual atom. All of the atoms of the same kind are known as the element. They're all structured the same, they have the same chemical properties, and so when we're talking about them in general, we refer to them as the element. You can really use the terms interchangeably, but I want you to know what they mean as you read or hear me using them through this topic. Now, all of the elements that we know of so far are organized into what's called the periodic table of the elements. Periodic means that there's a repeating pattern. And what we see in terms of the elements is that there are differences as we move from left to right across the table. And that as we move from one row to the next, the chemical properties of this element are the same or very similar to the one right above it. And then the same pattern holds true as we go across. Now, we're not going to need most of these elements when we're talking about biological organisms. But if you move into chemistry, then you'll see that those patterns do exist. What I want to focus on next is what information we can get from the periodic table. For any element on the periodic table, there are at least 3 pieces of information that we can see. The most obvious is the symbol for that element. In this particular periodic table, they've been very kind and they've spelled out the name of the element as well. So we can see that Be is the symbol for beryllium. Most periodic tables don't give you the name of the element, and that's okay. Just above the symbol for the element, we see this number. This is called the atomic number. And below the symbol for the element, we see what's called the atomic mass. All we need to draw any atom on the periodic table is the atomic number and the atomic mass. Now, before we get started drawing an atom based on what we can see on the periodic table, we need to talk about the 3 particles that every atom is made of. Those are protons, neutrons, and electrons. Now, protons are positively charged. You can remember that because both proton and positive start with P. Now, we refer to the charge of a proton as one charge. What does that even mean, to have one positive charge? Well, we use protons as the unit of measurement. Since we don't know anything smaller that has a charge, whatever charge a proton has is equal to 1. And anything beyond that is equal to 2 or 3 or 4 or something in between those numbers in terms of positive charge. So we're using the proton basically to define this. 1 positive charge. Protons also weigh 1 atomic mass unit. What's an atomic mass unit, you say? And it's basically like the pounds that we measure our own body weight with. Except if we tried to measure a proton in pounds, the number would be so small, it would have so many zeros before we actually got to a non-zero number that we would be lost. So we make up our own unit of measurement to measure something as tiny as these atomic particles. And once again, we use the proton as the unit. So whatever 1 proton weighs, that is now 1 atomic mass unit. And anything else is based on how much a proton weighs. Now, protons are located in the nucleus or the center of the atom. If we go on to neutrons, you might gather from the name that neutrons are neutral, meaning they have no charge. Neutrons, like protons, weigh 1 atomic mass unit, so they have the same mass. And like protons, they are located in the nucleus of the atom. So here you can see protons and neutrons clustered together in the center of the atom. Electrons are different. Electrons have a negative charge. Their negative charge is exactly the opposite of the positive charge that we saw with protons. In other words, they are 1 unit of negative charge. 1 electron will cancel out 1 proton in terms of charge. Now here I have the mass of electrons listed as 0 atomic mass units. That's kind of a little white lie. Electrons actually do have mass. It's just so small that it doesn't really matter. It doesn't have an impact on the overall mass of the atom. So let's just call it 0 and be done with it. Finally, electrons are located in what we call shells. The shells are represented in this diagram by these circles, and the electrons are traveling around this circle like a planet orbiting the sun. That's not entirely accurate. Actually, it's not accurate at all in terms of how electrons travel. They actually move sort of randomly in this entire sphere around the nucleus, but we don't have to understand that in terms of using atomic structure in this course. That's for chemistry. Okay, let's go back to the periodic table. I told you that the atomic number and the atomic mass were the only 2 things that we needed in order to be able to draw any atom. So let's start with the atomic number. The atomic number indicates the number of protons that any element has. The number of protons is how we identify the element. If we have 4 protons, we have beryllium. If we add a proton to the atom, then we've created another element. If we take a proton away, again, another element. So if it has 4 protons, it is always going to be beryllium. So the atomic number is the same as the number of protons. That means that we know that we have 4 protons, and we know that the protons are in the nucleus of the atom. So I've got 4 protons here kind of clustered together. Now, protons each weigh 1 atomic mass unit, neutrons weigh 1 atomic mass unit, and the electrons don't weigh anything. So we know that the overall atomic mass has to be the neutrons plus the protons. And since we know the number of protons, which is 4, we can take the atomic mass, which is 9, and subtract the number of protons, and that gives us the number of neutrons. Now, you're probably wondering how I went from 9.0122 to just a plain old 9. I'm going to talk about why the number that you see on the periodic table is not a whole number in the next video in this series. But for now, whenever you see the atomic mass here, you just round to the nearest whole number. So this is 9. Okay, so we have a total atomic mass of 9. 4 of those units are due to protons, which means the rest have to be neutrons. So over here, I have our 4 protons and our 5 neutrons. It really doesn't look like a square, but that was all I could manage with the software. So this is already the nucleus of our atom. Now, the next thing that you need to know is that all atoms are neutral. What that means is that the number of positive charges, or protons, has to be equal to the number of negative charges, or electrons. So if we have 4 protons, then we will have 4 electrons. Now, electrons are not located in the nucleus of the atom. They are located in these shells, these orbitals. And there are rules about how electrons get put into these shells. Each shell holds a maximum number of electrons. The shell that's closest to the nucleus holds 2. The shells after that each hold 8, at least up to a certain size atom. After that, this rule breaks down, but again, that's for a chemistry class. So the other part of this rule is that you must fill the innermost shell first, then move to the next and fill it before you can move to the next and fill it. I want you to imagine that we've got a giant electron family and they decide to go on a trip, and each one of these shells is like a car. The very first car that gets filled is, of course, the two-seater sports car, which is way more fun to ride in than all of these minivans that hold 8 electrons. So this fills up first. And once this is filled, the remaining electrons find their seats in the shells that are outside of that until we've taken care of all the electrons that that atom has. The outermost shell that contains electrons is known as an atom's valence shell. This is important because it's the electrons in the valence shell that actually do the bonding with other atoms. In other words, this is where the chemistry happens. Everything that's full and inside of that isn't really interacting. Okay, so for beryllium, we have our 4 protons, our 5 neutrons, and 1, 2 in the innermost shell, 3, 4 electrons. And now our atom is complete. Now, one more thing that's important about the valence shell. The number of electrons that we see in the valence shell tells us how many bonds an element can form. So this is the element carbon. Carbon has 1, 2, 3, 4, 5, 6 electrons. Now, those first 2 electrons ride in the sports car, the innermost shell, and the remaining 4 sit in the minivan. Well, remember that this has 8 total seats for electrons, and carbon only has 4. That means that carbon's valence shell has 4 empty seats. Each empty seat represents the potential for that element to bond. In other words, carbon will always form 4 bonds with other elements. Let me move my picture here. So carbon may form bonds with 4 different elements, 4 different atoms. It could have 2 double bonds like we saw in, actually we haven't seen it yet, but like you're gonna see in carbon dioxide. But again, 1, 2, 3, 4. Or it can have 2 single bonds and a double bond. But no matter what, every time you see carbon, it's going to have 4 lines sticking out from it because it has 4 empty seats, meaning that it can form 4 different bonds. Let's look at another example. Oxygen has 6 valence electrons. It has 8 in total, 2 of them in the innermost shell and 6 in the valence shell. Now, because that valence shell holds 8 electrons, that means that oxygen has 2 empty seats. And because it has 2 empty seats, it will always form 2 bonds with other atoms. Sometimes it'll be a double bond with just 1 other atom. Sometimes it will be 2 single bonds with 2 different atoms, but oxygen will always have 2. The take-home message here is that if you want to know how many bonds an element will form, you look to see how many seats, extra seats that it has. It's sort of like picking up hitchhikers. If you have 2 seats, you can pick up 2 hitchhikers or connect with strangers, other atoms. All right, that's it. On to the next one.